Okay, so here's where we were last time. We were talking about Gauss divergence theorem. Here it is. Right now I've got the theorem represented here on our diagrams, sort of our developing diagram. Our diagrams keep growing, getting bigger and bigger. Let me just remind you, the reason why I'm putting everything on these diagrams is as a sort of a mental organization tool, if nothing else. Right? I mean, having all these ideas put in a methodical way, on the page allows you to keep track of them better, if nothing else. Right? Of course, there is much more than that. Putting them in this methodical way on the page allows you to see patterns, and the patterns have actually led us to finding these various theorems. Okay. All right. So. What Gauss's divergence theorem says is that in the context of looking at three-dimensional regions with two-dimensional boundary surfaces, right, the divergence operator is the sort of complementary operator in the sense that if you take a three-dimensional region and look at its boundary, if you take a vector field and compute its divergence, then the flux of the field through the boundary surface is the same as the triple integral of the divergence over the original solid. Right, so there's what Gauss's divergence theorem is saying. And again, it's you can see what it's saying is that these operators are I don't want to say they're undoing each other, but they're complementary to each other. Okay. Just like all of our other boundary theorems. Okay, quick example. And I've already commented on this, but let me say it again. This is an equal sign. Equal signs go both ways. I don't know why it did that. Equal signs go both ways. So you can think of this as a tool for using, if you want to compute a flux and you do it with a triple integral, or you can think of it as a tool if you want to compute a triple integral, then you could alternatively do it with a flux. Most of the time, it's this. Most of the time, we're going to be interested in computing fluxes. And rather than parameterize and go through that whole game, the triple integral might be easier. Or, sometimes, we're going to see a lot of this today, sometimes it's just valuable to be able to make connections between different ideas. And the reasons for that, we'll see a bunch of examples today. Okay, a bunch of physics stuff. Okay, but first, just a good old, plain old computational example. Here it is. Let's suppose I want to compute a flux, and I am given a vector field, right? And I am given a surface. Note the orientation. Right, there we go. I want to compute this flux right here. How do we compute flux? Well, we've got ourselves a new theorem that says how to compute flux. You can compute flux with triple integrals. Now, another reminder, we talked about this last time, but big reminder, this is not just any old flux. You can't just pick whatever flux you feel like and say, I'm going to compute it with Gauss's divergence theorem. That surface, very critically, has to be a boundary of an actual solid. There needs to be an anti-boundary, in other words. That anti-boundary, and again, it's not a formality, that anti-boundary has to be there because it's the domain for the triple integral that you claim that you're going to convert this into. Right? So if your surface isn't a boundary, there is no triple integral. It's not that the triple integral is zero. It's that it doesn't exist. There's no such thing. The whole thing becomes garbage. Okay, so I cannot emphasize that enough. Make sure to check that. So we better follow our own advice here in looking at this question. We've got the unit sphere oriented outward. Here it is. Unit sphere oriented outward. Is that a boundary of something? Well, we just have to use our geometric intuition. This sphere, sure enough, no problem. This is a boundary. It's a boundary of this ball on the inside. Right, so the sphere is the boundary of the ball. Another quick reminder while we're here. Spheres are surfaces. Balls are solids. Right, so be really careful with that terminology. We say, if you want to talk about a solid, don't say sphere. Sphere is just a surface. All right. So this is a boundary, and therefore we can talk about a triple integral over the anti-boundary. So the flux through the boundary surface is the triple integral over the anti-boundary. That's what Gauss's divergence theorem tells us. Triple integral, that is, of the divergence. Now, in order to proceed, then we've got to actually do this calculation. Here's the vector field. Got to compute its divergence, like so. And it turns out to be just 2. Lucky break. Now, again, I arranged this example deliberately as a first example to, for good things to happen. Right? So, nice, easy constant. Okay, so we end up with an easy triple integral as opposed to what would have been a, non-trivial, maybe even hard flux integral. So, big win, easy computation. How are we doing? Is everybody on board? Okay. All right, so now begins a bunch of interpretations and kind of physics. We're going to do a lot of physics today. And those of you who are engineering majors, this is going to be crazy important for y'all. If you're not physics majors, if you're not engineering majors or physics majors, then think of this as a liberal arts broadening, right? And you get to learn some stuff that you may not have immediate applications of. But isn't that why we're in college, right? This isn't a vocational school. Okay. All right. So here's Gauss's divergence theorem again. Let me zoom here for effect. This Gauss's divergence theorem. This thing that I'm going to say is what we're computing. Now again, you can view it either way, right? But I'm going to say we're computing flux, and we're computing it with this formula. Okay. This thing that we're computing, this flux, I'm going to give it a name just for sort of convenience purposes. I'm going to call it capital Phi for flux, right? Which I think we've used before. Okay. So here's another way to think about what we've written down here. This flux, first of all, notice flux being a triple integral, we're saying that flux is an accumulating quantity. Now let's just take a pause on that for a second and remind ourselves, because, hey, wait a minute, I thought flux was computed on the surface. Isn't flux a surface that you give me a surface, I compute the flux? Right? Now we're saying here that it's computed in the interior. Right? So which is? Well, it's a little bit weird, but it's both. Flux is computed on the surface, but the observation that we made in proving this result is that even though it's computed on the surface, we can think of it as accumulating over the interior, right? Because the flux through this little piece of boundary surface plus the flux through this little piece of boundary surface, the interior edge cancels and you get the flux through this boundary surface. Right? So it looks like a boundary thing, but it's actually accumulating over the interior. The same way mass does. Mass accumulates. You give me a solid chunk, and if I chop it in half, these two masses individually, they add up to the original mass of the total. So mass is an accumulating quantity. It's a kind of a stuff, right? It's a physical, visceral thing. It's concrete. Flux behaves as if it is too. So that's a lot to digest, and that's something you should, this feature of accumulation is what, the algebraic manifestation of what it means for something to kind of behave like stuff. Okay. All right. So with that in mind, the accumulation of stuff, the total amount of stuff, is the accumulation of little bits of stuff over the interior. Now notice flux is equal to these two different things, and that means this. Right? And I want to look at this little equation down here. This says the amount of flux. Again, full recognition, we compute the flux on the boundary, right? But that's kind of an illusion. We only see it on the boundary. That flux is actually accumulating over the entire interior of the solid, and on some little piece inside that little interior, on that little piece, the amount of boundary flux that's happening on that little piece is computed as divergence times volume. Okay. And now I want to draw your attention to another formula that we've written down that's not terribly different. Now this is seemingly unrelated, but let's suppose we're computing mass. Nobody bats an eyelash if I write down mass, a dm is density times dv. Right? And this mass is density times volume. Well, of course it is. Well, that's just a different kind of accumulating stuff and its associated form of density. So the big thing that I'm leading up to here is that this being, this being mass, it makes a lot of sense to refer to this as mass density. Right? That's a common term. We use it all the time. There are other kinds of densities. There's population densities, etc. Right? So stuff per unit size, as applied in this context, that's what the density is. Okay. Well, along those lines, same idea. This being flux, it makes a lot of sense to think of divergence as flux density. That's just extending the analogy of this terminology. It's just another kind of density. We have accumulating stuff. Divergence is how much of that accumulating stuff exists per unit volume in a given region. It's a density. Okay. All right. Now, this term, flux density, I did not make this up. This is a very standard term. You'll notice here the title of this subsection, flux density. In my physics classes, again in that past life, I believe I heard the term flux density probably on the order of as often as I heard the term divergence, because that's what it is. And when you're computing divergence in a physics class, what you're going to do with the divergence is you're going to interpret it as a density and take a triple integral of it, just like this. Right. So flux density, very natural way to think of divergence. So for one thing, be very aware of this term, flux density. And for another thing, try to digest it. Try to internalize this idea that is a natural way. I mean, after all, again, we're talking about an accumulating quantity. This is the integrand of the corresponding triple integral, just like what we call mass density is. So why wouldn't we call this flux density? Okay, so a lot of good ideas in there. This is going to seem super weird, but I think this will be helpful in the lines of what we were talking about a second ago. You can do the same thing with the fundamental theorem of calculus. And, again, there's temptation to say, I already understand the fundamental theorem of calculus. I've got my point of view on the fundamental theorem of calculus. I don't need another one, right? But again, the purpose here is not to be able to make a use of the fundamental theorem of calculus. We want to get all the juice out of it that we possibly can. So it's going to help you, I think, in my opinion, in digesting this idea of divergence as flux density by doing the exact same thing here, right? So here we go, fundamental theorem of calculus. Let's look at the object that I claim that we are computing, and I know in practice we tend to use the fundamental theorem like that. Fine, okay, but in my analogy, we're interested in computing this quantity that I'm going to call change, and I'm going to use delta to represent change. We use delta to represent change all the time. Usually we modify that, but I'm just going to say delta because I want to think of it, again, as being a kind of a thing on its own. Okay. All right. Well, that means, in effect, then, that we're saying that little bits of change that happen along the along the interval over which we're looking are computed as f prime times the size of each little piece. And now I'll remind you that in this context, looking on an interval, we have another calculation that ends up with a similar result in the same way that d change is f prime dx. dm, if we were computing mass, would be delta times dx. And here we are again. Look, we have this, mass, And that leads us to interpreting this expression here as a mass density. Now, in this case, of course, well, we're not talking about mass per unit volume here. We're talking about like a one-dimensional rod that has a varying mass per unit length. Not volume, it's length. Context is length. So nevertheless, even though it's a modified notion, mass density is what delta is there. And along those exact same lines, this being now change as computed in the fundamental theorem, I offer what I think is a pretty cool interpretation of the derivative, and that is that it is change density. It seems, I know, look, I get it. That seems really unnecessarily awkward, right? Because it's so much easier to think of the derivative as slope of a tangent line, right? Well, you've got it drilled into you and there's benefits to all these different points of view on the derivative, right? But this is not really awkward, it's just unfamiliar. This is actually a really great way to think about the derivative. Maybe not for the kinds of applications that you saw in Calc 1 classes, right? But in this situation, I think there's just tremendous benefit to thinking of the derivative as being a kind of a density. It's a density in the interpretation of change as accumulating over the interval. It is playing the role of a density. All right. Now, I have another little diagram to offer here. By the way, I should have thought about this in advance, and I'm sorry it slipped my mind, but I have this as a PDF file, and I want everybody to have a copy of this. So I am going to email you the PDF file of this, as soon as class is over and I remember, so you don't have to feel the need to copy this down. But here we have a picture of a context where we're using the fundamental theorem of calculus. And I'd like to encourage, I'd like to point out how you can literally think of the derivative as change density as inspired by this picture. So here's our picture. We've got this function f, like that. There's a graph, of course, right? It's a graph of f. And we're looking at it over this interval from a to b. And on that interval from a to b, the function changes by, that amount, right? The function starts at that value and it ends at that value. So here's the change that we're talking about. Here's what if I write down f of b minus f of a as an integral of f prime, there's the thing there's this accumulating quantity. Okay, now I want to ask the question, where in the graph picture, where is the change? Now, looking at the formula f of b minus f of a, the change is computed. I have to look at a to get f of a, and I have to look at b to get f of b. And so I measure, you might say, I compute the change at those two endpoints of the interval. That's where I compute it. And now I appeal to your life experience of stuff changing. Is that where stuff changes? Does stuff change at the starting and ending points of the experience? No, of course not. Stuff changes continually over the time between when you start and when you end, right? So when I was, 5, right, maybe I was this tall. And then when I was 10, maybe I was this tall, right? What is f of b minus f of a there? Well, this is my starting height. This is my ending height. Did my height change spontaneously at those two times? Don't be silly, right? My height changed over the course of the time in between there, right? Little bits of change literally accumulated to add up to the total change in my height, right? So I think it is not only plausible, but almost necessary to view the change, even though the change is computed on the boundary. Yeah, sure, and that's algebraically that's where we sort of get it from. But where did the change happen? Well, for crying out loud, it happened right here. This function, that's where the change was happening. There wasn't any change happening there. There wasn't any change happening there. And it certainly wasn't happening at the two endpoints. Those are just points. Change happens continually. Yeah, everybody on board so far? Okay. Now, the finer distinction of, change happens over the interior, but explicitly where is the change happening? Well, again, it's happening, you see it in the graph like that. That's where the change is happening. So said differently, in the domain, the change is happening here. What is the giveaway? What is now visually the giveaway is obvious. It's changing. Look at it, right? But algebraically, what's the algebraic giveaway that change is happening at these points? And the answer is the derivative. The derivative is literally giving you how much change is happening per unit size, right? So on this little subinterval right here, how much change is happening over that interval? Well, there's the width of that interval, and here's the amount of change that's happening. And, I mean, again, very literally, the amount of change per unit size is the derivative. So, now again, you can think of that as a slope if you'd like, and again, it has its moments, right? But we're talking about the amount of an accumulating quantity that is fitting inside of this little bit of width, right? So the derivative is literally a density. It is stuff per unit size, and so right here, f prime is large. And that means that there's a lot of change happening around there, and you can visually see that in the picture. Over here, that point, f prime is 0, and this is your sort of algebraic indication that this accumulating quantity of change, it may be happening in the interior, but it's not happening there. Right? At that point, there's no change. So you can think of change as being not only sort of happening generically, sort of, overall in the interior, you can think of it happening in specific densities with the density given by the formula of f prime. Okay, all right, now why am I trying to enlarge your understanding of the fundamental theorem of calculus? That's not my ultimate goal. My ultimate goal is to leverage the fact that you have great intuition for the fundamental theorem, that you have great intuition for change, something we've all experienced a bazillion times in a bazillion different ways, right? I want to leverage that intuition and how you can see and get from this picture, this idea of an accumulation density, right? And let's then, by analogy, try to make sense out of that in the context of Gauss's divergence theorem. So I'm going to do the same sort of argument here. Let's talk about flux. Oh, by the way, now I've drawn a two-dimensional picture here. That's just I have two-dimensional paper, right? And it's hard to make three-dimensional pictures, especially when there's all this going on with the field arrows, and it's just not only harder to draw, but harder to see. Okay, so I've drawn a two-dimensional picture here, and I want you to just use your imagination. Think three-dimensionally here. Okay, we've got this region, and here's the boundary. And if I were to say flux of this vector field, here's my vector field. If I were to ask how much flux is there of this vector field over that surface, well, how do I compute flux? Well, I measure the flux on that boundary surface. That's the formula. That's where you measure it. Just like you measure change on the endpoints here. Let's not oversell this point of view. Right? You compute change on the boundary. Of course you do. But it's actually happening in the interior. And likewise here. Sure, we compute the flux on the boundary, but the flux is actually happening in the interior, and divergence is what's telling you explicitly where in the interior and how much. So, just as a sort of a for example, let me zoom in a little bit. Imagine a little piece. Let me do this, and I'll do it in dark blue. Okay, here's a little piece of my domain. And again, I'm drawing a two-dimensional thing. Think three-dimensional. Apologies for the artistic, limitations. Oriented outward, of course. That's a terrible little arrow. Let's improve that. There we go. So here is a little piece. Get this over here where I can see it better like that. And let's try to get a sense for how much of this flux that I measure on the boundary, how much of that flux is happening on that little piece right there. So I claim that there's actually kind of none happening at this point. And the way you can see that is look at the field lines. The field, on that edge, the field is perpendicular to the normal vector. There's no flux happening on that edge. Face. It's three-dimensional face. There's no flux happening on this edge. Face. Again, sorry, three-dimensional. On this face here, well, the field is like that. It's in the same direction as the normal vector, and so, we got to multiply and stuff, but yeah, there's going to be a significant amount of flux happening on that face, and it's going to be positive because the field and the normal vector are pointing the same direction. Okay. Whereas, over here, on this sort of back left face, let's call it, there's going to be a significant amount of flux. The field is, after all, pointing kind of, it's not perpendicular to the normal vector, but it's pointing the opposite direction. The normal vector is pointing that way. The field is going that way. So on, sorry, I missed the thing. On this face, we're going to have a large negative amount of flux. And now I appeal to your algebraic intuition. Check out the vector field. The vector field is, I was intending to draw it as being constant. Right, in this whole general area over here, the vector field's constant. And so that being these two edges, faces are the same size. These two bits of flux on this face versus this face are going to have the same magnitude. They have opposite signs. Grand total flux is 0. Okay. All right. So the flux is 0 there. I claim that if you were to write down a formula for this vector field and take its divergence, you would get 0. After all, there's no flux happening in there. No flux, no divergence. Okay. All right. Now let's take this same picture and let's just reconsider it over in here. Let's try to draw it straight. There we go. Okay. Same picture. And a lot of the same arguments apply. The vector field is perpendicular on that face to the normal vector. There's no flux there. I think my elbow hit the arrow button. Likewise, no flux here. Right? There's going to be positive flux there because the normal vector and the field vector are pointing the same way. There's going to be negative flux over here because the normal vector and the field vector are pointing opposite ways. But notice, in this general vicinity, the field's magnitude is increasing. We've got smaller field vectors there, larger field vectors there, and they're even bigger by the time they get over to there. So the magnitude's increasing. That means that there's more positive flux and less negative flux. So grand total over this entire subregion in there, there's a slightly positive amount of flux. And that's going to be evidenced by divergence being positive. So divergence, again, algebraically is going to tell you, where is the flux actually happening? The flux is actually happening in this region here. Divergence will algebraically be the giveaway there. We're measuring the flux on the boundary. Yeah, sure, of course we are. I mean, that's what the formula says. Right? We're measuring it on the boundary, but it's actually happening in the interior, and the divergence is what's telling you exactly where and proportionally how much where in the interior. Just like the derivative is telling you where the change is actually happening, even though, silly to say it, but even though, of course, you measure it on the boundary, but that's just how the calculation works. Okay, so I think this analogy is fantastic. I want to strongly encourage you, if you're trying to get your brain around the idea of flux density and why is divergence, why should I think of this flux density, and what does that help me visualize about what the divergence theorem is really saying, right? Think about the questions in this context, and then think about the analogous questions and points of view in this context where the answers are highly relatable. Alrighty. Okay, so going back to the book, there's another context in which we can talk about densities. Divergence is flux density. The derivative is change density from the fundamental theorem of calculus. What about Green's theorem? Does Green's theorem give us a notion of density, and if so, density of what? Yes, it does. Now, I do need to make a little bit of a case for what is it that we're computing here. There's Green's theorem. Let me zoom in. There's Green's theorem. This thing that I'm computing, what does that look like, and what should we call it? Well, so here's the idea. It turns out, now again, I'm just going to take you straight to the winning move here. The best way to make sense out of this is to think in terms of fluids. Even though it's a line integral, even though we're accustomed to thinking of line integrals, more so is computing work, and the fields are representing forces. Let's instead think about fluids. Okay, so this vector field here, I want to think of that as representing a fluid that's flowing along. And here, let me make it not constant. Okay, so there's a vector field. And this interpretation that we have of, as you're moving along a curve, some curve. Now let me just draw a regular curve for the moment. Here's some curve, right? As you're moving along a curve, the dot product in here, f dot t, and keep in mind there's TDS inside of the dx, is representing, okay, at a given location, how much is the vector field flowing sort of along the curve, right? This is our old interpretation of what vector line integrals mean in the context of fluids. How much is the fluid flowing along the curve? Okay. All right. Well, now, but wait a second. This isn't just any old curve, right? This is a boundary curve. Boundaries don't look like that. Boundaries have to close up, right? And here's the thing. What that means then is that being as this is a boundary, it has to, the direction that it's going has to make a full circle. Right? Look at those tangent vectors. If you drew those unit tangent vectors have to go all the way around. You can see that the loop goes all the way. That's how it loops back around on itself in the first place. Okay. So if the curve is making a full circle, and if we're measuring how much the vector field is, not exactly, of course, but kind of, sort of, at least, approximately in some sense, moving along with the curve. If the curve's going around in a circle, what we're kind of measuring is how much is the fluid flowing around in a circle the same way the curve is. Right? And so the term that we use here to represent this line integral is circulation. To what extent is the vector field kind of going around in a circle? To what extent does the vector field represent a fluid that's doing like this? Right? So circulation is a pretty reasonable term. everybody on board? It's just a point of view. It's a way of thinking about it. Again, by the way, this is a very common terminology. This is what they call it when fluids are going around in circles. I don't know about y'all, but my parents, when I was a kid, would talk about certain doors in the house had to remain open and certain other doors had to remain closed because of air circulation. Well, they're literally talking about the air going through the air conditioning system, into the intake, through the blah, 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 I don't know how those things work, and then coming out the air vents and going into the house and then getting sucked back into the air intakes, and we're literally talking about the air going around in circles. That's a fluid circulating. That's what we're talking about here. So this vector line integral is what computes how much of that circulation is happening. Okay. All right. So, this point of view. I'm going to use the lowercase Greek letter sigma to represent circulation. That's this line integral. That's what we're computing here with this formula. We made the observation that this, and at the time we called it boundary line integral, but let me now call it circulation. Circulation accumulates, right? That's where we got this double integral from in the first place, is that this circulation was an accumulating quantity, and it was accumulating over the interior. So the total amount of circulation is a accumulation of little pieces of circulation. And that tells me that we have another density quantity to think about, right? So in the same sense that this is circulation, likewise a pretty good physical, if you want to have a physical way to think of Green's operator, what is Green's operator? What does it look like? How do I think about it? It's circulation density. Okay. How are we doing? Does everybody see the analogy I'm talking about here? It's a lot to digest all at once here, I know. This is a really good lecture to capitalize on it being on the YouTube channel, right? So in other words, go to the YouTube lecture to the point where you're like, wait a minute, what was that? Pause it, think about it a little bit, scribble, go ask a question, ask a friend, ask me in office hours, ask the help room, and then listen to it again, make your way through the lecture like that. Okay. By the way, just another little cultural point, another common term for circulation density is vorticity, which I think sounds cool, right? Vorticity, a la the word vortex. Okay. All right. So I want to talk about another kind of physics now. We'll talk about different ways to think about divergence. In a sort of a more physical sense, instead of we've been thinking of it somewhat sort of geometrically right now. Flux. Okay, now let's talk about flux of what? And by the way, this is kind of a standard picture of flux right here. That there's, that flux means we have this, a positive flux, that is, means we have sort of an outward movement of fluid through a surface. Okay, now I would like to use this point of view on flux to make an interpretation, this time a physical interpretation of divergence. And here now, I want to be specific about what kind of a fluid we're talking about here, and what are the rules of this little game that I'm creating. We're talking about what I'll call kind of physical fluids. In other words, actual stuff that exists in the real world. So maybe we've got a gas, like air, right? And it's flowing. This is literally representing air flowing that way, right? Or, now this isn't going to sound like a fluid, but maybe we're talking about a flow of ants. And, we don't think of ants as a fluid. But, after all, air is made up of particles. It's a bunch of actual little teeny tiny little particles that are moving kind of somewhat together, thus defining a flow. So are ants. So, okay. Okay, so let's imagine that there's a bunch of ants in here, and then they start walking, they start moving around. Specifically, they start flowing like this. Well, I appeal to your physical intuition. If they're doing that, then the ants are leaving the circle. Right? The number of ants inside the circle is decreasing. Right? Okay. So let's write that down with math now. This is no big deal, but mass, ants, whatever you have, whatever your fluid is made up of. Mass is an integral of density. Right? Let's take a derivative of both sides and multiply by -1. That's perfectly legal. Not immediately clear why we want to do that, but we can. And now let's remind ourselves that this expression here, negative rate of change of that quantity, in this case mass, or again, population of ants, whatever, I don't care. That's what we were just talking about. That's the rate at which ants are leaving or the rate at which mass of the air is leaving this region, whatever it is. How much flux you have, right? How much flux you have tells you how fast the amount of stuff there is in the middle is decreasing. Right? So flux is negative dm dt in this context, this metaphor. Everybody happy with that? Ants leave, less ants. Right, that's all I'm saying here. Okay. All right, well, don't forget that flux is triple integral of divergence, and we just agreed from this little calculation here that negative dm dt is that triple integral, and that gives us a nice interpretation of divergence. Divergence, here, let me, oh, come on, I wanted the yellow. Okay, divergence, looking at the comparison of these two equations, divergence is how much the density is changing, right? A change in density you might think of as compression, but in this case, how much the density is changing negatively, and so I'm calling it decompression. Divergence represents decompression. That's the nice little punchline, right? Think of ants and how they are, if ants are leaving, if you have a positive flux, then ants are leaving, but then specifically, not only is the quantity of ants on the inside getting lower, but the density, locally speaking, at any given point, the ant density, ants per unit area, ants per unit volume, is going down as indicated by the divergence. How are we doing? Is everybody happy? So that's a pretty interesting physical interpretation of divergence. All right. Okay, now I've got another physical interpretation of divergence. It's a little bit different. We're going to create a different kind of physical metaphor, a different physical scenario. So now for my next thing here, forget about ants. We're going to think about a different kind of a fluid. We're going to think about a fluid where the density can't change. Right? So a pretty good example of this is water. You might have noticed I've been talking about fluids for a long time now, and I didn't bring up water. Didn't that seem weird? Well, water is a different kind of a fluid. Water's density doesn't change. Now, you might say, look, I've been down at the bottom of the swimming pool in my backyard, and my ears hurt when I get down to the bottom, but when I get up to the top, they don't. Surely the density is higher at the bottom. It's got all this water pressing down on it. Doesn't that make it higher density? No, it doesn't. The density of the water at the bottom of your swimming pool is pretty much exactly the same as the density at the top of the swimming pool. The pressure is higher, yeah. That's why your ears hurt. It's hydrostatic pressure. It's not density. Okay. So let's think about water now. And this conversation we're about to have is maybe, I'm going to say, less physical, but it's got physical, there's versions of this. But anyway, I like to start with water, even though this isn't actually how water works. there's a region, and let's consider, again, here's a sort of a standard picture of flux. Right? Well, what would this say if this is how water was flowing? What does flux mean in the context of water? Boundary flux, of course, we're talking about boundary flux. Does it mean that the density of water is decreasing in the inside? It can't. Density of water can't decrease. So there must be water must be coming from somewhere, right? If water is I went to the highlighter, sorry. If water is in the process of leaving this region, but the density is staying the same, the quantity of water is not decreasing, and yet there's water leaving, something must be refilling that region. Something must be a source of water inside of there. Right? So we call this literally a source. There is a water source. Now, again, I like to use water in this metaphor, but of course this is not physical at this point. If you have an enclosed three-dimensional region, water can't just spontaneously generate inside of there, right? But there are other fluids where stuff can spontaneously generate. Here's a nice example. Let's think about light. We can spontaneously generate the fluid that is light, right? Photons, the particles carry light. Right? Those light bulbs up there are spontaneously generating. Those are a source of this fluid that's flowing around the room here. That fluid being the flow of light particles. Right. So there are fluids that can spontaneously generate. Light's a nice example. Right. Sound, I suppose, maybe if you want to think of sound as a kind of a fluid, right? Then I'm spontaneously generating sound fluid as I speak, literally. Right. Okay. So I'm going to continue with water as the thing here, even though again, you can't spontaneously generate water, but it's nevertheless still a kind of a nice. I like it because it's easy to relate to the density of water being constant. Okay. All right. Now, first a little algebra. Mass is triple integral of density. I'm interpreting density as mass per unit volume. Okay. Let's take a time derivative of both sides of that equation. Perfectly legal. And get this. Perfectly legal. I just took a time derivative on both sides. And now, coming back to our metaphor, thinking of water flowing like this, and we've agreed that the amount of flux represents how much water is leaving this region, but if flux represents how much water is leaving, then that must also represent how much water is being spontaneously generated. How much quantity of fluid per unit time is being spontaneously generated. So flux is the total source rate over this interior region. Yeah? Okay. And, again, look at the algebra. If we have a physical sort of interpretation of flux as being the total source rate, then locally, pick some point in here. At that point right there, divergence must be telling me how much source per unit volume in that little subregion that I'm talking about. So source per unit volume, and I'm going to call that source density. So source density, source per unit volume there. So now that's, again, it's a different physical metaphor. We're thinking of a different kind of a fluid. We're thinking of some constant density fluid. The density doesn't change. Like the density of photons in this room right now is not changing. It's about how many photons are inside of this little volume right here. It's not changing at all. Photons are flying into this region, but then they're flying right back out. We're not accumulating photons in here, right? So the kinds of fluids where density is constant, but that can be spontaneously generated by light bulbs, for example, right? Divergence is source density. It tells you where the fluid is coming from, specifically. So, okay. All right. Alrighty. Okay, so continuing with physics. More physics. Y'all have seen, those of you who've had a physical science class in high school or whatever, know this formula for gravity. If you haven't had it before, no big deal. I assume everyone has personal experience with gravity, right? I find that I get more experience with gravity as I get older, right? This is the formula for it. It's an inverse square force, so you take two masses, the farther they are away, then the less gravitational traction there is between them, right? And it's specifically in a squared sense. So twice the distance gives you a fourth of the gravity. Okay. All right, so this is all scalar talk. We're talking about forces by simply telling you their magnitudes. Well, that's incomplete. Right? We're talking about a distance as if it's just a scalar, whereas it's much more thorough to talk about the displacement, the vector that is the difference of these two locations. Right? So, with that in mind, here is a vector version of the gravity formula, and this is what I'm going to call the gravitational field. We all remember the gravitational field, right? It's an example of a vector field. And here's what it is. Now, specifically, this is the amount of gravitational field that's created by a single piece of mass. You'll notice that I don't have the other piece of mass in there. So, true, right? I would like to think of the gravitational field, for example, created by the Earth as something that's intrinsic to the Earth. And if I want to know the actual force that it applies on me, then yeah, I got to multiply that by my mass, right? But the field itself doesn't depend on me. That's just me. Okay. So the field, no M2 in it, just the M1. And this looks wrong. A lot of students object to this formula. They see the cube and they say, hey, wait a minute, it was supposed to be inverse square. What's going on there? And I'll point out that I could rewrite this formula as negative G M1 over magnitude of X squared, and then times X over the magnitude of X. And so really all I'm doing with that cubed is I've got a convenient way to indicate a unit vector describing the direction, but the magnitude, what is the strength of this gravitational field? It is inverse square. Okay. All right. Okay, so here's a wonderful fact. And this is something you can calculate on your own, but here's your formula for the gravitational field. There's some constants in it. So just go along for the ride. But if you compute the divergence of this gravitational field, you get 0. It's super weird. 0. And the consequences of this fact are huge. There are a lot of consequences of this. A quick disclaimer, of course. Now, notice this vector field is completely undefined when x is 0. And so, in other words, if you have a little piece of mass, at where that piece of mass is, the vector field that I'm using to describe the gravitational field, it's undefined. It doesn't exist. And this is one of the flaws of thinking of mass as coming in single points, not physical, right? Here's some mass. It's not located all at a single point. It's distributed over space. Of course it is. But anyway, so that's I've got to put that confession in there. But away from the mass, this is very physical. This is if you're far away from where the mass is, whether it's tightly sort of compressed into a single, very small ball, it's kind of indistinguishable between that and it actually being at a point. Okay. Alrighty. So let's see some consequences of this. We're going to start off by looking at this scenario. Here is a point mass. And that mass creates a gravitational field. Gravitational fields point toward the mass. As you all know, they get weaker the further you get away. Closer they're stronger, further away they're weaker. Okay. And now let's suppose that I have a solid region here. solid region. And that solid region, of course, has a boundary. And now here's the hard question I'm going to ask. This is going to seem like a really hard question. This lumpy solid's boundary, this strange surface that is this boundary, if I want to know the flux of the gravitational field through that boundary surface, oh my gosh, look at that gravitational field. The direction's constantly changing. The surface is a weird shape. It's going to be hard to parameterize. This is going to be a bummer to compute. I mean, if I parameterize it, plug it into the vector field has square roots in it, right? Magnitude of x is a square root. Worse, that square root is cubed. Oh, man. Right? A direct calculation of the gravitational flux through that surface would be brutal. Okay, so here's a better way to do it. We will instead observe very conveniently that flux, you've asked me to compute flux. Well, flux is, given that we're talking about the boundary of a solid, right? That is I mean, that was the question here. It's a boundary of a solid, right? Wrong color. This was a boundary, and so I can use Gauss's divergence theorem and write this as a triple integral. That flux is a triple integral of the divergence over the interior solid itself. Oh yeah, don't forget the divergence is 0, and bam, we are done. We just did that whole tremendous calculation in, what's that, 3 steps. Flux is 0. Everybody on board? Okay. All right. Now, there's a detail devil that I need to talk about here. That is, very importantly, I assumed here that the mass was located outside of the region. That really matters. No pun intended. The reason that matters is because I need to be able to cite the divergence theorem over this region. In order to cite the divergence theorem, the vector field has to be defined and continuous and differentiable and continuously differentiable inside of that region, and where the mass is, it's not, right? So if I had mass sitting in here, then the resulting vector field would have a gross discontinuity there. Gauss's divergence theorem would not apply, and the whole calculation on the previous page would crash and burn. Okay. All right, so now let's consider what can we do in this scenario where the mass is on the inside of the region. Okay, so the clever move here, and this is going to give us a partial victory, but it's going to be nevertheless important. We're going to consider a different region. The different region is this region. We're going to cut out a little cave for that mass to live in. Right? We're going to look at this yellow region here called R0. R0 is that yellow region, and the mass is not included in R0. Therefore, the flux through the boundary of R0 of the gravitational field is obviously 0. No problem, right? The gravitational flux through the boundary of R0 is 0. The thing is, the boundary of R0, let's talk about that. What is the boundary of R0? The boundary of R0 has 2 chunks. The boundary of R0 has boundary of R, but the boundary of R0 also has that sphere that I put in there, and awkwardly, it's the inward-oriented sphere, not the outward-oriented sphere. So I'm going to say minus S. Okay, so that's the boundary flux that I computed. I have computed the flux through this surface. And that's not what I wanted, right? I don't want the flux through that surface. I want the flux through just this one. So I've got this extra term in there, this S term that's kind of messing things up. Okay, so all I have to do then is just confess I've computed the flux through the boundary of R0, which consists of the boundary of R minus S. I still got 0. Here's the partial victory. This thing that I wanted to compute now, the flux through just the boundary of R, I don't have an answer for it, but my partial victory is I know that the flux through the boundary of R is the same as the flux through S. Because the difference is 0, therefore these two fluxes are the same. Okay, why that's a partial victory is that argument would apply equally well no matter where that mass was. Let's, for example, so here's our mass again. Let's suppose the mass is at that location, and then I surround it by this sphere. And I make my argument, and I get that the boundary flux through the outer boundary is the same as the flux through that green sphere. Okay, now, different question. Let's suppose I was interested in the mass being up there. Right? Well, I would draw a little sphere around it, and I would make the exact same argument. And I would get the exact same answer. If the mass was way up there as opposed to way down here, I still get the same result that the flux through the outer surface is the same as the flux through that little green sphere. And you can see it doesn't matter how I move this mass around, that little green sphere, wherever I put the mass inside of there, right, that flux through that green sphere is always going to be the same. So the very important punchline is, when you have mass on the inside, the outer boundary flux isn't 0, but it is independent of how that mass, where that mass is, or how that mass is distributed. Distribute the mass however you like, I don't care. How you move the mass around doesn't matter. Okay. All right, now here's why that matters. We're going to consider now another hard physics problem. This is going to seem overwhelming, highly implausible. Let's suppose now that I don't have a single mass, but let's suppose I have a distribution of mass. And it's a non-constant distribution, so I'm trying to draw it as being there's more mass kind of concentrated in the upper left and kind of less mass over here. Okay. So lots of mass distributed over lots of volume. That's going to create an ungodly gravitational field. Notice each little atom of mass in there is going to create its own little gravitational field. Right? And so that one, yeah, but then this one over here, this little atom over there is going to create its little gravitational field. So does every other, there's trillions, right? Bazillions of atoms in this distribution of mass. Each one's creating its own hard to write down gravitational field centered at different locations. So there's shifts and all these things. It's going to be nightmarish to write down this gravitational field. Right? And now here's what I propose we do. Again, it seems highly implausible. I propose that we come up with a formula for what is the divergence of the gravitational field. That's the total gravitational field created by all of that mass. Surely you're joking. Right? I mean, all of it? There's too many. How could I write them all down? So we actually have the tools to do this. It's not even all that hard of a calculation. Believe it or not, we just have to be really clever, and we're going to use the results that we just got through talking about to do it. So here's the idea. I'm going to first consider a slightly different question. I'm going to look at a teeny tiny little sphere somewhere there inside of this distribution of mass. There's a little teeny tiny little sphere. Couple observations I'll make about this sphere. Everything's uniform in that little sphere. It's a very small little sphere, right? So the density is constant. The density is way different over here, and it's way different over here, and it's way different over there. But over that teeny tiny little sphere, come on, the density is approximately constant. And so is everything else, approximately constant. For example, the divergence, this mysterious divergence I'm trying to calculate, it's approximately constant inside of that little sphere. Okay. Okay, so here's how, now next thing I'm going to do is I'm going to ask the different question of what is the flux through that little sphere. That's not our original question. Our original question was to compute the divergence. I'm going to compute the flux. Okay. All right. Well, we have powerful results about flux. All the mass that's outside of our region, poof, don't care, gone, puff of smoke, doesn't matter. The mass that's inside of our region, I don't really care where it is. I just care how much there is. So this is I can take this tremendously intimidating scenario of all these different little pieces of mass, all with their own gravitational fields that are all kind of at different locations. And I can just say, oh, well, all this mass, let's see here. So all this mass that's on the outside, bye-bye, don't care. That mass does not contribute to the flux that I'm interested in. And then furthermore, inside, now let me expand just for, just for visualizing purposes. Inside the sphere, teeny weeny little sphere, right? Inside that sphere, yeah, sure, there's a bunch of mass at a bunch of different places inside that sphere, but I can rearrange that mass however I like. It doesn't matter where the mass is inside the sphere, just how much there is. So I'm going to say, look, all the mass that's inside the sphere, let's just concentrate all of it exactly at the center. Same amount of mass, just exactly at the center. And now let's compute this flux. And that's not a hard problem at all. I've got a single point mass. It's a sphere. It's got crazy symmetries. This is going to be a convenient calculation now. Again, reminder of something that's not exactly what I wanted, but we'll get to that. Okay, so let's compute this flux. The flux through that sphere is, here's the calculation. There's our formula for flux. Here's the alternative way to write that formula for flux. Remember, our ds vector is just kind of a shorthand for little n ds scalar. Okay. And, our gravitational field, we have a formula for it. There it is. Our normal vector, well, it's the normal vector points in the same direction as the position vector. It's just a unit vector. By the way, reminder up here. Position vector, right, points in the same direction as the normal vector. Right, so take that position vector and divide it by its own magnitude. Spheres are awesome. Spheres have just crazy symmetries. All right. Now more good fortune happens. Let's look at, these are constants. They'll pop right outside of the integral. Now let's look at what's left over in the integrand here. I have a bunch of stuff there in the integrand, but notice x dot x is magnitude squared. I have magnitude squared divided by magnitude to the fourth. What I have is 1 over magnitude squared. And don't forget the magnitude of x is the radius. So I'm just going to call rho. And notice that that radius is constant. Again, aren't spheres wonderful? Spheres have so many crazy cool symmetries. Rho is constant. Magnitude of x is constant. So 1 over rho squared. So that, I'm sorry, I was going to call it r. Sorry, r for radius. There we go. Yeah, everybody on board? And now all we're left with, this really nice simplification. We're just interested in surface area. Surface area is 4 pi r squared. That's an old geometry fact from high school geometry class. And the r's cancel. And son of a gun, here you go. There's your formula for that flux. And as promised, it only depends on the total amount of mass. Right? Doesn't matter where that mass is distributed. Knock yourself out. Distribute it however you like. Just however much mass is enclosed in that sphere. Multiply by this constant, negative 4 pi g. That gives you the flux. Okay. Now, yeah, but that's not what we wanted to calculate. We wanted to compute the divergence of this horrific vector field. Right. Okay, sure. Let's talk about the divergence. Here's another calculation of that same flux. We will get to divergence in seconds here. Flux is a triple integral of divergence. The divergence is, as we just agreed, approximately constant on that ball. It's a very teeny tiny, itty bitty little ball. Approximately constant. Factor it out. All that's left is volume. Right? So this flux thing that we've just calculated, we just computed the same thing two different ways. That means that these two answers are equal to each other. Solve for divergence, and we're done. Divergence is, you take the negative 4 pi gm and divide by the volume. Mass divided by volume gives you density. So we didn't have to deal with this overwhelmingly intimidating vector field that we're computing the divergence of. Flux has these wonderful properties that we capitalized on. We computed flux using awesome properties of flux. And then we noticed that there's an easy relationship between flux and divergence. Okay, so that's a really nice calculation. The consequences of this are huge. Let me remind you of this formula here. This formula only applies to spheres. Right? Very importantly, in this calculation that we did here, in all that calculation, we used the symmetries of the sphere like hugely in order to be able to do that calculation. So this is just for spheres as I've derived it here. But now I know a formula for divergence. Knowing a formula for divergence, I can take a triple integral of both sides. Divergence being that, take a triple integral of both sides of that equation, and what you get is flux is again just proportional to mass. So you have to take this intermediate step of computing the divergence and then doing an arbitrary triple integral over it so that you can change the shape of the solid. But you do get this punchline, and this works for any solid whatsoever. Okay. How are we doing? Is everybody on board? Okay. All right. So I want to make a couple of quick comments. I have 60 seconds, and I think I can do this. But there is a theory of physics that I'd like to point out, and I think this is great for visualizing gravitational fields. There is a theory of physics that mass communicates its gravitational force by way of a little tiny particle called a graviton. Sounds weird, right? Why can't gravity just be gravity? Okay, there's a creepy aspect to gravity just being gravity, and that is, wait a minute, the mass is way over there. It's not touching me. How could it possibly pull me toward it if it's not even touching me? How does my mass know that there's mass over there anyway? This action at a distance thing is a really serious problem, very disturbing, and a lot of people are very rightly unsettled by this. Right? So the one way to resolve the idea of action at a distance is that, okay, yeah, my mass and that mass over there, yeah, my mass is shooting out little particles called gravitons, and if I hit that other piece of mass with that graviton is the messenger that says, hey, this way. Right? That the force is communicated by the graviton. Anyway, that's the theory. So what I'd like to point out then is that this suggests that gravity behaves like a fluid, and that's super weird to say, right? That gravity behaves like a fluid. But I just want to point out super quick all the instances that we've already seen of gravity behaving like a fluid. It's inverse square. If you have, here's another fluid, light, right? If you have a light bulb, how bright that light bulb appears to be, how much brightness you get on a sphere that's expanding. If the sphere is twice as big, you have 4 times the area, and therefore the light hitting the sphere is 4 times as dim. It's inverse square. If you have a light bulb that is outside of the mass, if you have a light bulb that is outside of a surface, what's the flux of light through that surface? Well, any photon that goes in promptly goes right back out, and the amount of flux in is the exact same as the amount of flux out. So the flux is 0, just like with gravity. And you can go on down the list. In fact, you look at this formula right here, what this says is, again, from a sort of a fluid's point of view, this says the way gravity is communicated, how much fluid is being created, how much source of gravity is there? Well, the source of gravity is mass density. How much gravity per unit volume, source density, flux density, right? Gravity per unit volume is mass per unit volume. Or even more literally, gravity is created by mass. Right? So this graviton point of view, think of gravity not as this, thing that keeps me falling down all the time on planet Earth, right? Think of gravity as a fluid that's being shot out by mass in the same way that light is shot out by light bulbs. Think of gravity as being basically like the flow of light. And all of these equations just start to make lots of sense. Right? So this doesn't prove that gravitons are real. The physical world doesn't obey our musings, right? But it is kind of plausible. Y'all have a great weekend. See you later. And I do have to, some of y'all came in after I started. Let me check you off on attendance.